All right, so we're going to start by talking about the basics of the electromagnetic spectrum. So guys, the electromagnetic spectrum, it's made up of all forms of electromagnetic radiation. So electromagnetic radiation are, radio waves. You've all heard of radio waves, microwaves, infrared, visible light, which, hey, visible light. How do you memorize visible light in order? Red, orange, yellow, green, blue, indigo, and then that is violet. Okay, Roy G. Biv. Roy G. Biv. Okay, ultraviolet, X-rays, gamma rays. Now, these are in order of wavelength, in order of frequency. The one thing that's not shown on here is energy. Which way does energy increase on the electromagnetic spectrum? Towards gamma or towards radio? Towards gamma. The energy is increasing this way. Okay? All right. All forms of electromagnetic radiation, what do they have in common? Do they all have the same frequency? No. Do they all have the same wavelength? No. They all travel at the same speed, the speed of light. And if it's a vacuum, right? If it's a vacuum, the speed will be 3 times 10 to the 8th, which is this c right here, okay? So I put up here on the screen the wave equation. C equals, remember this symbol here is wavelength, and then this is frequency. Basically, this equation is velocity equals wavelength times frequency, but if you're dealing with electromagnetic radiation in a vacuum, the V becomes C. Does that make sense? Now, if all of these travel at the same speed, right, that means the velocity is the same. The velocity is the same. So what's the relationship between wavelength and frequency? Well, a big wavelength, if your wavelength is big, then your frequency would have to be small. And then vice versa, If your frequency is big, your wavelength is small. See, and that's what they're showing you here. See, wavelength increases to the left, frequency increases to the right. All right. Now, all forms of radiation are made up of these little bundles of energy called photons, right? So imagine, you have a beam of light, like the light coming out of the projector right there, and I reach up and I grab a little tiny bundle of that light called a photon. All forms of radiation are made up of these little bundles called photons. So the equation for the energy of one photon, like one single photon, this is the equation right here. The energy of a single photon, one photon, equals h times frequency. Now this h is Planck's constant. Did I spell that right? I'm a bad speller. Planck's constant. You know what? I don't think there's a C there. P-L-A. Oh, man, I should look at Planck's constant. Now, Planck's constant. Do you have to memorize it? No, it's going to be given on the test, even on the multiple choice. Planck's constant, now notice there's 2 versions of it right here. We have this version and we have this version. Now, what's the difference between these versions of Planck's constant? Well, the first one is in terms of joules. The second one is in terms of electron volts. And you know what? I think I briefly mentioned the electron volt back when we were doing like electric fields or electric potential. But look, what is the electron volt? It's a very, very small unit of energy. Now, why are we talking about such a small unit of energy? Because the type of problem you're going to be dealing with, you're going to be dealing with an electron moving from one energy level to another energy level. Does that involve a big amount of energy or a ridiculously small amount of energy? Extremely small. But just so you know, the electron volt, the conversion to joules is this, and it's a very easy conversion to remember, because what do you recognize here? The 1.6 times 10 to the negative 19? That's the same number for what? The charge of an electron. So 1 electron volt is equivalent to 1.6 times 10 to the negative 19 joules. So we have two versions of Planck's constant. The first one uses joules, the second one uses electron volts, and then this here, H times C. Now look, you could figure that out by yourself. You could take H and multiply by C. What is C? 3 times 10 to the 8th meters per second. Now, why might you want to have HC? It's right here on the data table for the AP exam. If you look at the table of constants, underneath Planck's constant, they give you what HC is. And let me show you why. The reason why, so if you take this equation for the energy of a photon, so let me clean this up. You take the equation for the energy of a photon. Now look, the speed of light is wavelength times frequency, correct? That just comes from this equation, right? So C equals wavelength times frequency. Solve this for frequency. Frequency would be C over wavelength, right? So take that, plug it in for the frequency. What do you get? You get E equals HC over lambda. So there's the HC right there. We're going to use it in a few minutes. All right, is this making sense? So look, what happens to energy if frequency goes up? What happens to energy if the frequency goes up? It goes up. Energy and frequency are directly related because H is a constant, right? H never changes. So if your frequency goes up, the energy goes up. How about wavelength? A big wavelength, a long wavelength would mean what about the energy? That would have to be low energy. Because what does a long wavelength mean? So look at this equation here. C equals wavelength times frequency. C is a constant. So if you have a big wavelength, if your wavelength is big, what must be true about the frequency? Small. And if your frequency is small, your energy is small. And you can see that in this equation here. If your wavelength is small, the energy will be small. Okay? Now, the type of problem you're going to be seeing. This is what you're going to see. They typically do this on the free response. So the Bohr model of the atom, you might remember from chemistry, the Bohr model of the atom is where you have those rings around the nucleus. The rings are referred to as energy levels. And what lives in the energy levels? Electrons. And the atom you want to think about is hydrogen, because hydrogen is the simplest of all atoms. What makes hydrogen the simplest of all atoms? There's only one proton, and if the hydrogen is neutral, one electron. So I want you to imagine one electron cruising around this nucleus, okay? And the nucleus, it has a positive charge because protons are in the nucleus, okay? If the electron is as close to the nucleus as possible, meaning in this first energy level, so see we have n equals 1, first energy level, second energy level, third energy level, fourth. The n's in this diagram indicate energy level. If an electron is as close to the nucleus as possible, we refer to that as the ground state. Close to the nucleus as possible is ground state. Now, is it possible to take that electron that's in the ground state and move the electron to a higher energy level? Is it possible to do that? Yes. And what do we call it? What do we call it if the electron is not as close to the nucleus as possible? That's called the excited state. And look, is there only one excited state? No. I mean, what if the electron would have gone, so instead of having the electron go out here, what if we moved the electron to like the n equals 3? Would that be the excited state? Yeah. Anything that's not the ground state is the excited state. If the electron is not as close to the nucleus as possible, that's called the excited state. Now, how does this all work? To move the electron from the ground state to an excited state, what needs to happen? It's kind of like if I take my coffee mug right here and I move it from this tabletop up to the top of this cabinet here. So from the tabletop up to there. It's kind of like that, right? Like, because does the electron want to leave and go farther away from the nucleus? No, because the nucleus is positive, the electron's negative, they like to be together, right? So if we're going to pull the electron away from the nucleus, what needs to be added to make this happen? Energy. The way this happens is this. To get this electron, in fact, let me erase this. So this hasn't happened yet. The electron is sitting here in the ground state. To get this electron to an excited state, what's going to happen is this. We're going to have a photon. So this little dot right here represents a photon of radiation, okay? The photon comes in, and what's it carrying? What does the photon have? Energy. The photon has energy. Bam! The photon hits the electron, gives the electron energy. The electron goes to an excited state. Depending upon how high does it go, well, it depends upon how much energy the photon had, right? So, okay, now, once the electron is up here in the excited state, is it going to stay there forever and ever? No. What will eventually happen? The electron will fall back down to the ground state. Now, dudes, is it going to fall down in only one possible way? How many different ways could this electron get down? Well, there's multiple ways. The electron could fall all the way. Now, what's going to happen when the electron goes back to the ground state? What's going to happen? Energy is going to be what? Released. It's going to be like this. When that happens, energy is going to be leaving the atom in the form of what? A photon. Radiation. Photons are radiation, right? So long story short, how does an electron leave the nucleus to the excited state? Energy gets added to the atom in the form of radiation, photons. When the electron leaves the excited state and falls back to the ground state, energy is going to be released by the atom in the form of radiation. You getting this? You are so not. Turn off 2048. You're playing 2048. Turn that off. Okay. Oh, don't lie to me. Now look. Hey, is this right here? Is this the only way the electron could have fallen back down? No. What else could the electron have done? The electron could have done that, taken a little break, then done that, right? It could have done it in 3 steps. Or maybe it could have done it in 2 steps. Maybe it could have gone like boom and then boom. You know, it can like fall to a lower energy level, take a break, and then fall again. Okay? Now, on the AP test, they're not going to give you these diagrams like the one on the left. They're not going to do it this way. They're going to give it to you like this. Okay? And I want you to realize this diagram on the right, it's the same as the one on the left. It's just like this. Ready? Here's the first energy level, second energy level, third energy level. See that? Like that. Simple. Okay, a couple terms we haven't talked about yet. Ionization state. Okay, so let's look at this diagram here on the right. The nucleus would be down here. This would be the nucleus right there. And then here's the ground state, right? You got like an electron there cruising around on the first energy level. If we took this electron and boosted it all the way up to here, this level up here represents where the electron is completely off the atom. If you take an electron and pull it completely off the atom, what did you just do to the atom? If an atom loses an electron, what does that mean? It became an ion, right? It became a positively charged ion. So this top state here is referred to as the ionization state. Notice that it's labeled 0, right? Electron volts. The other thing I want you to notice as you move away from the nucleus, the energy levels have more energy. It's kind of weird. So notice we're starting with -12, and then we go to -3. What has more energy, -12 or -3? -3. -3 has more energy than -12. and then we go to negative 0.75. So the energy is increasing as you move away from the nucleus. It's just like, dude, when I take my coffee cup, there's my air. What happens when I move this away from the Earth? The energy gets greater, okay? Now, specifically, how much energy, for this diagram here, how much energy would be required to ionize this atom? To take this electron from the ground state and move it all the way up to this, to the ionization state. How much energy would we need to add? So we have a photon coming in, bam, hits that, oh, oops, wrong thing. I haven't hit in the nucleus. Okay, turn it, hits the electron. How much energy would this incoming radiation need to have to boost the electron off the atom? This incoming photon would have to have what? 12 electron volts to get it all the way up to there. Does that make sense? And then we refer to that amount of energy. That amount of energy is referred to as the ionization energy. Okay, so let's look at a problem here. This is from last year's, this is from the 2013 AP free response. So we only have a couple minutes. I'm just going to go, this is, yeah, typically they put these questions on the FRQ. Typically this is on the free response. Okay, so we have the energy level diagram for an isolated atom is shown above. Okay, a collection of such atoms with electrons in the n equals 3. So they're telling us that we have electrons sitting here on the n equals 3. Undergo transitions in which the atoms only emit photons. Well, duh, that's how energy is going to be released in the form of radiation. Radiation's made up of photons. And the electrons eventually end in the n equals 1. On the diagram above, draw arrows to indicate all possible transitions. So what are the possible transitions for this electron in the n equals 3 to go to the n equals 1? What are the possible transitions? It could go all the way, like that, straight down to the n equals 1. And then what else could it have done? It could have gone like that, taken a little break, and then dropped the rest of the way. Those are the possible transitions right there. Okay? And that's what they're looking for. Okay, B. Calculate the longest wavelength. Okay, guys. What are they talking about here for longest wavelength? What's another term, or how else could you describe longest wavelength? I'll give you a hint. C equals wavelength times frequency. C is a constant. Longest wavelength is the same as what? Shortest frequency. Hey, will you close that back door? Hey, I own you guys for a couple more minutes. Don't get up. Longest wavelength is the same as what? Shortest frequency. Shortest frequency is the same as what? I'll give you a hint. E equals HF. H is a constant. Shortest frequency is the same as what? Lowest energy. So what they're saying when they say longest wavelength refers to shortest frequency, which is what? Lowest energy. Okay, so which of these is the lowest energy? How much energy is this guy right here? Let's see, negative 12 and 0.75. How much energy is that guy? 11.25 electron volts. How much energy is this guy right here? 0.75 and 3. That's going to be what? 2.25 electron volts. How much energy would this guy be? 9 electron volts. Which one's the lowest energy? 2.25. Now, how do you get wavelength from that? 2.25 electron volts. How do we get the lowest how do we get wavelength from that? Well, dude, combine these two equations together. I showed you this already. What do you get? E equals hc over wavelength. So wavelength is going to be hc over E. So hc It's a given. It's on the data table. It's earlier in the lecture. Take your HC, 2.25 electron volts. That'll come out as wavelength. All right, let's just end with part C here. What is the ionization energy of the atom? So they're talking about you got an electron down here, right? The nucleus is right there. How much energy is needed to ionize this atom? To get it all the way up to there? We need 12 electron volts. The answer to this one is 12 electron volts.